Okay, now I want to talk about figuring out the angle between two vectors. Sometimes it's not really obvious, like in the last videos where we had the two drawn. Sometimes you're given them in Cartesian form. So give me a second here. So what if you have two vectors, or perhaps they're 3D, right? When things aren't simple and you can't just draw the picture and then do a little bit of math to figure out that it's 135 degrees, what happens? So we've got two brand new vectors. The first thing I would do is probably sketch these to kind of get a feeling for it, but it's hard to sketch in 3D. I'm going to try my best here. So maybe what I'll do is I'll draw this. So maybe I'll call this the x-axis, this the y-axis, and then I'll say out of the page is the z-axis. So you have to kind of use your imagination here a little bit and imagine this is coming out of the page. The way I'll try and draw this one is I'm going to, again, have this be the negative x-axis over this way. This is the negative y. And then this kind of slanted axis, you're imagining it's going into and out of the page. This is tough, right? So let's just check. X goes to Y, goes to Z, out of the page. Looking good. All right, so in this case, let's try and draw the A vector. It goes 3 to the left, or negative 1, 2, 3, up 4. And then to indicate that this is in the XY plane, what I'm going to do is draw this and this. So this is kind of showing you this goes to the y-axis, this goes to the x-axis, and I don't have a line drawn to the z-axis, so it's not in the xz plane. Now I'm going to try and draw this vector, which is down 2, a little bit less, and then it kind of goes out 5. 1, 2, 3, 4, 5. So that's the vector B, and this is the vector A. And if you try to get it, you can't get a protractor on this, one's out of it, and it's really hard to get the angle. So how could we figure this out? Well, one thing we can do is maybe go back to our definitions of multiplication, which I think are over here. Okay. We saw that there were two ways to multiply vectors. I keep filling in a little bit more here. There's the dot product, which gets the angle involved, and the cross product, which gets the angle involved. Which is easier to work with? The dot product is always easier to work with because you don't have to deal with the direction. The other thing that's special about the dot product is when you use this to figure out angles, it doesn't require as much thought. Sine inverse on your calculator always outputs numbers between positive 90 and negative 90. Whereas cosine, right, we can actually get angles between 0 and 180. And I just basically, trust me on this, use the dot product for some reasons that I just discussed that you don't have to understand. Let's go back to our board. Basically, use the dot product. Nobody uses the cross product to get the angle between. They end up making mistakes. All right, so here we go. What I'm going to do is use the definition like this. Oh, let's get some marker crazy here. Getting serious. The caps are coming off. Here we go. I know that A dot B should equal A dot B. You may be saying, this seems really dumb, dude. Just give me a minute. Trust me. Okay. The idea is we're going to write one side in components and the other side using our angle formula. So, for example, we know that you could write this as A, B, cosine of the angle between. That is what we want to find. Write that in blank. This is a good idea. We're getting this involved. That's what we want. On the other side, I'm going to write it as AX and AY, BX and BY, and I'm going to add those together. Oh, there's another term, isn't there? AZBZ. There we go. So now, if you know these two definitions of the dot product, we can get the magnitude of each vector. I can get the components of each vector. And in fact, we already have that. if I plug all this stuff in, all I have to do is isolate this term, take cosine inverse. And that's exactly what we're going to do. I'm going to divide through by AB, the magnitudes, and then I'm going to take the cosine inverse. Of all that jazz. What was it? Let's see, AX, AY, AZ, BX, BY, BZ, all over AB. And that, you could just memorize this formula, but for me, it's a lot easier to just remember there's two ways to write the dot product and do some math. Right? For me, this is a lot easier. This process is a lot easier than memorizing something, but you do what's right for you. If you're like me and if you have to be one of my students and take my tests, a lot of times what I tell you is this is not on your equation sheet, but there's no reason that you can't have this like memorized and maybe be looking at it on a note card. And then right as I hand out your test, you can put away the note card and then scribble this on the front page of the test, and that doesn't offend me. So if there's ever some weird piece of information that you feel really helps you to memorize it, that's how you can get through my tests. I'm fine with that. As long as you put the note card away before you scribble it down, that's pure. I'm cool with that. All right. So now in this case, let's go through the math. Ooh, actually, let's start plugging in some stuff that's zero. Look at vector A. There's an I hat, a J hat, but there's no K hat component. So that means this term goes to zero. That's not too bad. There's no I hat term, no BX. So for this one, this goes to zero. So really, it's not as bad as it looks. This is typically how these work out. Anytime at least one of your components is zero in a vector, the math is pretty quick showing you the techniques that I use. All right. So my math is designed for problems like physics, where usually at least one component is zero. All right. So in this case, I need to get the magnitude of A and the magnitude of B. I'm going to figure those out in my calculator. If you don't remember how to get the magnitude, you can go back and watch it. Well, I'll just do it for you. I don't care. A, which is the magnitude of that, should be the square root of AX squared plus AY squared plus AZ squared. Do you remember that? That's how you get it. So I'm going to grab my calculator. So the idea is if it's this one, well, that's just fine, isn't it? Meters, because it's got units on it. The magnitude doesn't have any I hats or J hats because it's just the side of it. This side is 5 long. The I hat and J hat is these arrows. Okay, you can get the B. I've got to punch that into the calculator. It's very similar. So in this case, it's going to be square root of what? -2 squared is 4 plus 5 squared is 29, 25. Whoops. What'd you get? 5.385. If you're curious, like, how come this 2 doesn't matter that much? Anytime one component is much bigger than all the rest, the magnitude is almost always very close to that. So yeah, it's just a trick. So this actually seems reasonable. 2 does not change much, right? The length of this side is almost the same as the length of that side, is what I'm saying. Right, this side's 5. This is only a little bit longer than 5 because this is so small compared to 5. All right. So now what the heck were we doing? Oh, we're trying to get this stupid angle. All right, so let's work this out. I forgot what we were doing. Okay. AYBY. AY is 4. BY is -2. So that should be -8. Well, let's just write this in. AY is 4.00 meters. BY was -2.00 meters. Sometimes it's good to see it written out once, right? And then A and B, notice those also have units of meters. And I guess that's what I wanted to show you here. By keeping this to 4 digits, our final answer should be good to 3, at least. So now, notice, here's what I was saying. Even though these all had units on them, they all cancel out. Meters over meters, meters over meters. So this makes sense. The argument of a function or an inverse function should have no units. So I get -8 divided by 5 divided by 5.385. Whoa, 5.385. So I get negative blah, 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 blah. I'm going to take cosine inverse of that. And I get 107.28. Because the first digit's a 1, I'll keep an extra one, but we're probably good to 3 here. So it's about 107 degrees. Let's just round it to 3 at this point. Let's say it's 107 degrees. Now, point B, if you had tried to do this same math with the cross product, 1, it would have been a lot harder. It would have been more tedious. And 2, almost everybody would get this wrong because when you punch the numbers into your calculator, it's only going to spit out an angle between you'd be off basically by 180 degrees. So I think you get something like -73, which is not the right answer. Okay. So what have we just figured out? That this weird angle between these two lines was 107 degrees. Oh, is there anything else I want to say about that? Oh yeah, I have a special corollary as well. Perhaps more common might be the following. Let's go over here. Whoops. What if you want the angle to an axis? So the trick is, let's say you want to get the angle to the positive vertical axis. What you do is you make one of the vectors positive j hat. You wanted the angle to the negative horizontal axis, you can make something negative I hat. But what does this do? Right? We get theta AB equals cosine inverse of AB. That's the magnitudes. And then we're going to get AX, AY, AZ. And we're going to get BX, BY, BZ. We're going to have some parentheses and some plus signs. This is the equation we just derived. If you want, you can rederive it. But look, it's not that bad. What is the magnitude of B? That's 1. What was the magnitude of A? That was 5.00 meters. Right? And then we could look at these things. The BX should be 0. BZ is also 0. And BY is 1. So notice you basically take the y component over the magnitude and cosine inverse to get the angle to the positive y-axis. Okay, if you wanted to go to a negative y-axis, you'd have a -1 somewhere here. All right. So in this case, I might as well do it because we're right here. Where's my calculator? There it is. Clear. Okay, so when I rock this out, I'm going to basically get AY is 4. So 4 div 5. I'm going to cosine inverse that. And I get 36.87. Oh, and this would usually we wouldn't call this theta AB. We would call this theta. What did I say? Y, because we're going to the y-axis. We could say the angle to the y-axis for this particular vector would be 36.9 degrees. All right, so that's how you can modify this to get the angle of the axis. Basically, just use a hat vector here. Good to go. All right.